let's calculate the standard entropy of a reaction. And we will define that as delta S, little superscript 0, that tells us standard, and I write Rxn for reaction. So this is the same formula that we saw for calculating the standard enthalpy of a reaction, where now we take the sum of the entropy of the products minus the sum of the entropy of the reactants. And here I've got an example for us. And of course, to calculate this, we're going to have to look up those standard entropy values of these molecules, and we would get those standard entropy values, in a table such as this. So I've got a reaction here: aluminum oxide plus 3 hydrogens makes 2 aluminum solid. So it reduces that aluminum oxide and water. So once again, we'd have to look up all of the values of these formulas. Okay. So I've done that already, and I'll write those values down. So for the H2O gas, it's 188.8 joule per mole K. For the aluminum solid, it's 28.3 joule per mole K. So it makes sense that our water is higher in entropy than our aluminum. It's a more complicated molecule. Our aluminum oxide, Al2O3, is 50.9 joule per mole K. And our hydrogen, our H2, is 130.6 joule per mole K. Now, it's also important that we are able to look at this reaction and make a prediction. So if I was making a prediction, I would see here that I've got 1 plus 3, so that's 4 moles of molecules. And it's becoming 2 plus 3, which is 5. So I should see an increase in entropy when I calculate this, because I'm going from having 4 molecules to now 5 molecules. But all the same, let's calculate it just to make sure. So we have all the standard entropy values that we've looked up, or that I looked up ahead of time. And now we'll apply this formula. So first, we've got to sum up the products. And we also have to take into account the number of moles. So we'll do the aluminum first. Okay, so that's going to be 2. Let's see here. Yes, so that'll be 2 times the 28.3 plus the 3 times the 188.8. And that's the sum of my products minus the sum of my reactants. And then for the aluminum oxide, that's there's only one of them, so it's just 50.9 plus 3 times the 130.6 for H2. So let's do it. Let's calculate these things up. So 2 times 28.3, and I'm just going to keep track of all my numbers here so I don't goof it up on my calculator. So that's 56.6 plus 3, let's see here, 3 times 188.8, and I don't know why we got that extra crazy 1 over there. That's not necessary. So that's 566.4, and then now let's just quickly add that to the 56.6. So that gives me 623. And that's going to technically just be joule per Kelvin in my units. And then now minus, and of course I'm going to have 50.9. And so let's say 3 times 130.6. Okay, and that's 391.7999 plus 50.9 equals, so this now was all 442.7 joule per Kelvin. And you can see when I subtract those, I am going to get a positive number. Okay, so 623 minus 442.7. And yes, I get 180.3 joule per Kelvin. What's important is that that's a positive number for my delta S of reaction. And that tells me after this reaction has gone, it has overall increased the entropy of the system, which makes good sense because there was 4 molecules at the beginning and it became 5 molecules at the end. So we should expect to see an increase in entropy of this reaction.